States of matter and intermolecular forces are a very important topic on the AP exam. Here's a review of gases. I talked about this a little bit in the stoichiometry unit. There are a good many multiple choice questions that could deal with gases. Notice I've bolded some of the parts of this out. If the temperature is not changed in a question, no matter what else they're telling you, the average kinetic energy of a gas does not change. Do remember though, if the temperature is constant, gases don't all have the same speed. They all have the same energy, but their speed is based on their mass. The lower their mass, the faster they would move to maintain that same average kinetic energy, which is kinetic energy equals 1/2 mv squared on the formula sheet. All gases will start to act like a real gas or non-ideally if it's at low temperature and high pressure. At low temperatures, the gases really don't have that much energy. Some of the IMFs, if they're polar especially, might start to come into play and cause them to not move as much as they normally would. And at high pressure, the gases at high pressures, gases would be in a very small volume, and the smaller the volume, we're assuming that the container is the gas's volume, but the smaller the volume, the gas itself is taking up some space in the container that we're not allowing for, so that causes some differences for using PV equals nRT. Again, stronger intermolecular forces could affect polar gas molecules. You don't have to know Charles, Boyle's, all those different names of the laws, but you should go through and remember just the effects of each one. Like pressure and volume are inversely related. Pressure and temperature and volume and temperature are directly related. And then the last picture here is Avogadro's law, which is the relationship between volume and moles. If we have an increase in moles, the pressure and temperature being constant, that volume will also increase. Here's just a little review of bonding, because this is one thing we'll be talking about with states of matter. There are the three types of bonds. These are intramolecular forces holding substances internally, like their individual structure together, ionic. The attraction between cations and anions. Covalent is that sharing of electrons, and metallic bonds have that characteristic C of electrons. When we talk about intermolecular forces, and this is where I use the abbreviation IMF, inter meaning between, we're only going to use this with molecules, not with metals, not with ionic bonding. So again, it's just with molecules. So these are things we would draw a Lewis structure for, and we're talking about the attraction between one structure and a neighboring structure. So here's IMF abbreviated. To know what type of IMF different molecules have, we really need to know their Lewis structure, because we have to know if they're polar or nonpolar. Okay, number one, London dispersion forces. You're welcome on the AP exam to abbreviate that LDF. That is an acceptable abbreviation we recognize. All molecules, and these could be polar or nonpolar molecules, do have LDFs between their molecules. However, it's the nonpolar molecules where this is their only force of attraction, and depending on how many electrons the molecule have, these can be significant. All right, we always assume LDFs are the weakest. They can be the weakest, but there are sometimes some situations where these can be stronger than expected. So if you're asked to designate why one nonpolar molecule has stronger London dispersion forces than another, I've underlined this is what we're looking for. Don't tell me it's about mass. It's about the number of electrons. The more electrons in an electron cloud, the more polarizable the cloud, and the stronger the London dispersion forces. And the stronger the forces, the more energy it would be required to melt or vaporize that substance. Dipole-dipole the name tells you, a dipole refers to something being polar. So this is an attraction between two polar molecules. It has the example there of H2S. Notice the partial signs. You cannot say sulfur has a negative end and a hydrogen has a positive end. You must say with polar molecules it's partially negative and partially positive, or it's incorrect. Same thing with when we talk about water. But water, like the molecules in the bottom, is connected by hydrogen bonding. So it's the force of attraction still with two polar molecules, except the polar molecules have three very electronegative elements that cause the hydrogen in the molecule itself to have a polar bond. So notice here on adenine that the nitrogen is that the hydrogen is connected to a nitrogen, and so we're looking for fluorine or oxygen or nitrogen because those are the three most electronegative elements. So that hydrogen has a very polar bond, which causes it to have a very partial positive charge, and the nitrogen would be partially negative. And it makes it be able to have a very strong attraction with the oxygen on the neighboring molecule. So again, we're looking for a hydrogen connected internally to an FO or N, and then having a hydrogen bond attraction, which is the IMF, to that oxygen across. And then you also see another example below. We have nitrogen. The hydrogen here is also connected to a nitrogen, but then it's attracted to a nitrogen on the neighboring molecule. Ion dipole. This is the attraction when we say something like NaCl, this is what's in the picture, dissolves in water. What happens is the NaCl, that solid, energy absorbed to break it into separate ions, the hydrogen bonding, some of that is broken up, and then exothermic attraction of ion dipole is occurring. So we can still use Coulomb's law to describe this relationship. If the higher the charge on the ion, the greater the attraction it would have with water, or the smaller the ion, the closer it would be to the water molecule, therefore it would have a greater attraction. So those are the two components of Coulomb's law. Make sure you could draw, this has been on the AP exam before, it gave you an ion, you had to draw water molecules correctly oriented around it. Again, do not say water has a negative and positive end. It's partially negative and partially positive. The physical properties of liquids like boiling point, vapor pressure, even solubility can be attributed to the intermolecular forces between the molecules. So if we say a liquid has a high boiling point, we're really saying it has some type of really strong IMF. We'd need to name that specific type. But also remember, if a liquid has a high boiling point, indicating strong internal intermolecular forces, that means it would have a low vapor pressure. Not much of its vapor would be forming above its surface, which water is a good example of this bulleted point. Common graphs that go with this. Notice the top graph. It has two curves. Just take a look at the axes. Kinetic energy is on the X, and fraction of molecules are on the Y. The higher temperature is actually the more spread out curve. A way to tell this, in this case, it has this dotted line that tells you the minimum kinetic energy needed to reach the vapor phase or to escape the IMFs. So as you can see, if the temperature is higher, that red shading under the curve is greater, more of the molecules have more energy, more are going to be forming a vapor. And we could tell the steeper hill is a lower temperature. Obviously, these may not be labeled if this was given to you as a question, but you should recognize the more spread out curve is the higher temperature, and then the taller hill is going to be the lower temperature. And as you can see, there's fewer molecules in that blue shading that have enough kinetic energy to be vapor. This is the vapor pressure graph, and the question is, why is diethyl ether, which I've given you that, you'd be given that formula. You're not really expected to, this just has the name written. You're not really I'm sorry, that's ethyl alcohol. Here's diethyl ether. You're not really expected at this point to, have to know that on the AP exam. You need to recognize structure. The oxygen in this structure gives this a polar place in the middle, but these CH3s on each end are areas of nonpolar where LDFs could occur. So you can see that it has the lowest boiling point of the three, and again, the definition of boiling point is where the vapor pressure of a substance equals atmospheric pressure. So notice that dotted line is 760. That's atmospheric pressure, 1 atmosphere at sea level. So the question is, why is diethyl ether having a lower boiling point than water? It's got to be about IMFs, but you can't just say that. You have to have specific reasons. So diethyl ether has these weaker dipole-dipole forces of attraction between its molecules. Again, you should see that oxygen on a carbon compound and know it's a polar area. If we saw an OH, like with the ethyl alcohol, it would have an OH on the end, then that we would indicate hydrogen bonding. But because these weaker dipole-dipole forces are only connecting it compared to the stronger hydrogen bonding between water, it's going to take less energy to break those weaker dipole-dipole forces between the diethyl ether molecules than, so therefore it would boil at a lower temperature. But we can also use IMFs to talk about certain types of solids. The only type of solid that's really held together by IMFs are molecular solids like water as ice, sucrose, which is sugar, table sugar, dry ice, which is frozen carbon dioxide. Anything that we would draw a Lewis structure for, or we're given, as you notice here, sucrose, you're not expected to be able to draw that, but you can, just see they'll give you these structures, and you're expected to, based on the different functional groups that are attached. Again, you don't have to know the names of these groups that cause substances to be polar in this category, but you really need to look for, and I don't call this a hydroxide, because when it's attached to a carbon, it's actually called a hydroxyl group. But when you see a carbon compound that contains, again, like I said earlier, an oxygen or an OH attachment, these are polar sites, and as you see, this is how water can come in and hydrogen bond at these OH places, and that's depicted here. So that's why such a large organic molecule is soluble in water, because it has many sites of hydrogen bonding, which causes it to be soluble. Again, this isn't breaking up into ions like an ionic solid is. It's soluble solely based on its ability to form a hydrogen bond with many water molecules. Notice other properties. They're not good conductors. They do melt at low temperatures because, again, IMFs aren't a very strong attraction compared to bonding. They can dissolve in water if they're polar like water. And again, as I said, you have to name the specific IMF. Ionic solids are held together by ionic bonds. The ionic bonds are very strong. Ionic solids have very high melting points. We can compare those melting points using Coulomb's law between different ionic solids. Ionic solids are not conductors unless they're molten. Again, we need free moving ions for them to be a conductor, moving charges. If an ionic solid dissolves in water, again, we talked about it splits into ions. It would have ion dipole attractions with water. If you have ions dissolved in water, that solution is a conductor of electricity. Covalent network, this is kind of a smaller category. You have these kind of giant molecules that are different atoms only covalently bonded together. So covalent network, a network of atoms to form a huge molecule. So we don't really use an IMF term here either. It's just very strong covalent bonds. If you look at the examples, diamonds, sandpaper, it's things that are have really strong covalent bonds. Metallic solids, this is where we talk about the sea of electrons, mobile or delocalized electrons that are free to move in the structure. Here's a good depiction of what a solid metal picture might look like. Again, don't use IMFs here. If we're melting a metal, we're breaking metallic bonds. And again, the properties of metals are, good conductors, malleable, ductile. They have luster, meaning they're shiny, and they do have relatively high melting points. Phase changes, this is just changes between the states. I also had this in another review topic, I think it was in the enthalpy, just because, when we're going from a solid to a liquid to a gas, those processes are going to need to absorb energy to break IMFs for this to happen. So they're endothermic. And then the second example is if we're going the other way from a water vapor to a liquid to ice, the solid, those processes release energy so the IMFs can take over and hold the substance together. A couple of distinct labs that go with IMFs are chromatography. This was actually a short free response question a couple years ago on the exam, which was probably the first time I could think of in the last 14 years had been on there as a free response. Again, if you just, the basics things you need to know is that chromatography is typically where you have a liquid which is traveling up a paper. So whatever's traveling up the paper is called the mobile phase, and that's going to be your solvent. The stationary phase is whatever the solvent's moving through. Usually it's a filter paper. Some schools use coffee filters, just some kind of paper, chromatography paper. Typically what you're trying to do is use a mixture of dyes and separate them based on their polarity. My class did use Kool-Aid and we could see what dyes were made up of Kool-Aid by how they traveled and separated themselves on the paper. It could be ink. There's lots of things, but the dye that travels the greatest distance up the paper is most attracted to the liquid, the solvent going through the paper. So the dye that travels with the solvent is most attracted to the solvent. The dye that stays lowest on the paper is most attracted to the paper. And we'll look at a picture of this on the next slide. Distillation is just a process of, you have a mixture of liquids with different boiling points. If we have the right lab setup, that we could boil the liquids, whichever liquid boiled at the lowest temperature would vaporize first. We could collect the vapor, let it condense, and this would just be a way to separate a mixture. So here's the chromatography paper that's shown here. Notice they put water, it looks like, as the solvent. There's an ink spot. As the water soaked up the paper, and notice the water went all the way to where it says that line, the water level, and the dye separated into yellow, this kind of hot pink, and then this bluish color. So again, whichever stayed the lowest was most attracted to the paper. Whatever moved the highest was most attracted to the solvent. And you can calculate something called a retention factor. Again, retention factor is just describing which dye moved the greatest distance. And then here's an example of distillation. You would be boiling in this round bottom flask. The first vapor would go down this condensing tube and be cooled, and it would actually drip into here. So again, this would only work if you had two liquids that had different boiling points.